Hello everyone, I remain your tutor, Mr. Life Changer. I am here to continue with the series I started on heat capacity, specific heat capacity, latent heat. Okay, this is the part 3. Okay, so here number 15, we have 100 grams of steam at 100 degrees Celsius is condensed and mixed with 400 grams of water at 10 degrees Celsius. Which expression correctly applies to the principle of heat exchange for this scenario? Now, even though I've not said anything about this, the answer is A. Now, the reason is because the 100 gram of steam, or let's say steam, has to become water first of all. Steam at 100 degrees Celsius has to become water at 100 degrees Celsius, that's to condense, before it now reduces to water at 10 degrees Celsius. Yeah, so at 100 degrees Celsius, here, this process of conversion is called ML, latent heat. In this case, latent heat of vaporization. I'm going to explain it better as we go down, okay? And while this one is MC theta. Whenever there is a change in temperature, the heat change is MC theta. But whenever there is no change in temperature, during phase change, we call it phase change, PHASE, change. During a phase change, there is no change in temperature. Phase change means the point where a substance is changing from one phase to another, maybe from liquid to solid, from solid to liquid, from liquid to gas, from gas back to liquid, and so on and so forth. Okay, and that is very, very important. I'm going to talk more on that. There is a section for that as we go down. Yeah, but the answer to this question now is the heat loss is going to be ML plus MC theta. Okay, then while equal to the heat gain now is going to be MC theta, because the water gain heat. Okay, that's very important for you to know. But that's, by the way, A is the answer. I'm going to just follow through and you will get it. The next one here says a 0.1 kilogram piece of copper, C equal to 400 joules per kilogram per Kelvin at 180 degrees Celsius, is placed in a 0.4 kilogram of water at 15 degrees Celsius. The calorimeter has a heat capacity of 40 joules per Kelvin. Calculate the final temperature. I already taught you this in the last video, and I hope you have watched the last video before coming here. We say that the heat lost by copper, in this case by copper, is equal to the heat gained by water, okay, then plus heat gained by calorimeter. As long as there is a calorimeter, you must add that value. Okay, so the heat lost by copper is mass of copper, specific heat capacity of water, copper, then the temperature change, which is theta 1 minus theta m. Since this is the hot, it means that the temperature is higher than this. Watch the previous video, I explained this. Then heat gained by water will be mass of water, I call it M2, specific heat capacity of water. The temperature change of water will be the temperature of the mixture minus the temperature of water. In the last video, I explained that whenever you mix a hot and a cold substance, the final temperature will be lower than the hotter substance, but will be higher than the lower substance. Okay, and that's why we have this. Then the heat gained by calorimeter plus is the mass of calorimeter, let me call it M3, specific heat capacity of calorimeter. Then the temperature change of calorimeter is the same as the temperature change of the water it contains. Never forget that. That is the rule. Okay, so with this formula you have done a good job. Now the mass of the copper here is 0.1 times the calorimeter, the specific heat capacity is 400. Then the temperature, initial temperature is 180, then minus, we don't know what the temperature of mixture is, the final temperature is, then equal to the mass of water is 0.4, this is it here, 0.4 of water. The specific capacity of water is a constant value, that is 4,200, not given, but you are expected to know that. The temperature of mixture is what we want to know, then minus the final temperature, that's of, the temperature of water is 15 degrees Celsius. So that is what we have here. Then plus, we are not given the mass of calorimeter, we are not given the specific heat capacity, but we know that mass times specific heat capacity is the same thing as heat capacity. So I can replace this MC now with 40, which is the heat capacity. Then you have theta m minus 15. Okay, so if we multiply this now, this is going to be 40 into 180 minus theta m. Now is equal to, and this time this is going to give us 1680. Okay, theta m minus 15, then plus 40 theta m minus 15. Okay, this is quite interesting. So this is now 40 into 180 minus theta m is equal to, since they have the same in the bracket, this another way you can do this. You can just simply add 1680 plus 40, and that will give us 1720, I guess. Yes. Then theta m minus 15. That's allowed in mathematics. Since they have the same term, you can just add the coefficient. It's allowed. Okay, so don't take it. Now, one of the ways I can simplify this possibly is to divide both sides by 40. I can choose to open the bracket, that's fine, but I'm also a mathematics teacher. There are many ways to achieve this thing. Okay, so I can choose to divide both sides by 40, and this is going to be 180 minus theta m equal to, this is going to be 43 into theta m minus 15, and this is going to be 180 t minus theta m equal to 43 theta m minus 43 times 15 should be 600, 450, should be 6,450. So 180 plus, if this crosses over, 6,450 is equal to 43 theta m plus theta m. Okay, so this is going to be 6,630 equal to 43 theta m plus this will be 44 theta m. Okay, so that means the temperature of mixture is going to be 6,630 divided by 44, which I don't know. This is 1, this is minus, this is 223. 44 divided by 223. Well, I am not with the calculator here, so you can just use your calculator, check what the final answer is. You can drop it in the comment section. Okay, now the next one says an electric heater. We've done a lot like this before, but not bad. Let's do it again. An electric heater of resistance 10 ohm carries a current of 3 amperes and heats 0.6 kilogram of a liquid for 5 minutes. The temperature rises from 20 degrees Celsius to 65 degrees Celsius. Calculate the specific heat capacity of the liquid. Okay, so in this case here, we say whenever you have a case like this, we are given resistance, we are given current, and we are given time. We can use the formula. Remember, we say that electrical energy is equal to heat gained. Okay, is a case of conversion of energy where electricity is used to produce heat, so you can equate them according to the conservation of energy. So electrical energy in this case is I squared RT, because that's what we have, and heat gain is simply MC theta. So the I squared, now the I is current, which is 3 amperes, so 3 squared, this is the current here, times the resistance is 10, times the time is 5 minutes, which you can write as 5 times 60, equal to the mass of the water is 0.6. Specific heat capacity is what we want to find. Then let me take this up. Then multiplied by the temperature change of water. Water changed temperature from 20 to, the liquid, not water, sorry. The liquid changed temperature from 20 to 65. So that's the change in temperature is 65 minus 20, which is 45. Okay, so this is going to be 9 times 10, 10 times 5 times 60, equal to 0.6 C times 45. Well, I can divide both sides by, I can say C equal to 9 times 10 times 5 times 60. You know, I'm not using calculator. That's the reason why I would have multiplied this, then divide. So you can always do that. Now, because I'm not using calculator, I try to find a way I can, make it easy to solve. Like, for example, now 45, 9 times 10 is 90. That means it will cancel this 2 times. 0.6 will cancel this, and that will be 100 because of the point. So 2 times 5 is 10. 10 times 100 is 1000. So the answer is 1000 joules per kilogram per Kelvin. So this is simply a mistake here. Because I don't think we made any mistake in our calculations. Okay, so that is it. That is by the way. Yeah, no mistake here. So that leads us to the next one. It says a 12 volts 5 amperes heater heats a 1 kilogram of a substance for 10 minutes. The temperature rises by 72 degrees Celsius. What is the specific heat capacity of the substance? Okay, in this case now, the electrical energy, since we are giving voltage and current, is going to be IVT. That's the electrical energy. And why the heat energy is MC theta, as easy as that. So the current is 5, V is 12, the time is 10 minutes, that means 10 times 60, okay, equal to the mass is 1. We are looking for the specific heat capacity. The temperature rise is 72. So we'll say C is equal to 5 times 12 times 10 times 60 divided by 72 to find C, okay. So I think 12 times this is 720. That will make here 10. 10 times 10 is 100. 100 times 5 is 500. So the answer is 500 joules per mole. Joules. Sorry, 500 joules per kilogram per Kelvin. So the answer to this question is A. Okay, so we move to the next one, not C. Okay, so the next one says an electrical heater supplies 4500 joules per minute to a 0.5 kg metal block. After 3 minutes, the temperature has risen by, that's the change in temperature. What is the specific heat capacity of the metal? Well, in this case, we can just say heat is equal to MC theta, since we are given the heat already. That means 4500 is equal to, the mass is 0.5, specific heat capacity is what we are looking for, and the temperature change is 90. It rises by 90 degrees. So this is 500. 0.5 times this is going to give us 45 C, okay. So C now is going to be 4500 divided by 45, and that is going to give us 100 joules per kilogram per Kelvin. We don't have the options here, but the answer is 100. Okay, there's a lot of mistakes in the options. So that leads us to the next one. The next one says a 24 volt supply drives a current through a heating coil immersed in 0.8 kilogram of water. The current is 2.5 amperes and the temperature rises from this to this in 8 minutes. Calculate the percentage of electrical energy converted to heat in water. Ooh, okay. Since we are asked to calculate the percentage, it means that not all the electrical energy was converted to heat, not all. So we are going to calculate them separately. This is how to think like a science student, okay? So since we are asked to find percentage, usually it's supposed to be 100% of electrical energy will be converted to heat energy. We equate it. But in this case now, we are asked to find the percentage. What that means is that there's a possibility that not all of the electrical energy was converted to heat energy. So in that case, I'm going to find electrical energy first. Electrical energy, since we are given voltage and we are given current, we are going to use IVT. The current is 2.5, the voltage is 24, times the time is 8 minutes. 8 minutes is 8 times 60. Okay, so this is going to be okay, let me see, 4 times is 10, 20. Let me leave it this way. Okay, I think I can get a calculator here. Give me a second. I just remembered I have a phone close to me, so let me quickly calculate that. Okay, so 2.5 times 24 times 8 times 60 is 28,800. So 28,800. Then now for the heat energy is definitely mc theta. So the mass is 0.8. The specific heat capacity, it is water, so the specific heat capacity is 4,200. Then times the temperature change from 18 to 48. 48 minus 18 is 30. Okay, that's the change in temperature. And this is going to be, so you have 0.8 times 42 times 30. This is giving me 100,800. Are you seeing what I'm saying? Joules. So you see, they are not the same. Only a fraction was converted to this. So now that simply means that the percentage conversion is going to be, I want to be sure I'm doing this correctly. Okay. 2.5 times 8 times 60. Okay, so this question seems not to be correct, and that's because it's expected that this one should be higher than this, but what we have here is different. 4,200, this is 0.8 kg, 24, 8 minutes, 8 times 16, 2.5. Okay, there's a problem with this question, but the percentage conversion is supposed to be the heat energy. That's the heat energy, whatever the heat energy is, divided by the electrical energy. Okay, will now be equal, times 100. That is supposed to be the percentage conversion. First of all, is an error for the electrical energy to be more than the heat energy. So the question is not correct. The question has a problem here, but this is how to go about a question like this. Okay, now the next one says the next one talks about the latent heat of fusion. I'm going to make a separate video for that because of that, so watch out for the part 4. Thank you very much.